Hello guys, this is Sumadhu here. We'll be talking about in this video maintenance and reliability, which happens to be chapter 17 from the 12th edition of Operations Management by authors Heisen, Render, and Munson. This chapter is pretty interesting for the fact because of its applicability. If we talk about, first of all, why do we need to learn maintenance and reliability? First of all, because when you have this, when the stakes are high, you want some of the components in the manufacturing or the services to be working, and the easiest thing to remember the concept from this is, let's say if you were to talk about, let's say, doomsday or any such thing. Let's say if you talk about the flashlight, or let's say a power generator or something, what is the probability that you'll have the power when you actually need it? This is time and time again very important for critical things such as in service sector like hospitals, wherein on the time of the exam we do need the power in the let's say operation theater or things like that. So I'm going to give you a few examples here. Maintenance, reliability. Okay, so the first thing is if you are into the electronics, there are concepts like and or. Okay, so to give you an example, where's my okay? If an individual component, for example, in this case, we are given individual component is 0.9 and is in series with another component 0.8 and is in series with another component 0.99. Okay, now there are a couple of ways to look at this. One way to look at this is the flow of the current or the flow of the water. Okay, if you look at the flow of the current, it's incoming, then this box has to work, and it works 90% of the time, and then it moves on to the second box or second component, which works 80% of the time. Then it moves on to the third stage, which works 99% of the time, and only then you have some result at the end. In terms of service sector, the way you can look at this is in terms of different people or different departments working together, such that some people or departments have a probability of success rate or working the day and the time when you need 90% of the time, 80% of the time, and 99% of the time. Only then you have some resulting output here. Okay, so if the moment the language reflects the fact that component A, component B, component C has to work, all of them have to work, so you'll have an output at the end here only if the component A and component B and component C, they all work. So in this case, based on the AND principle, you would multiply the probabilities to get the resulting probability. So in this case, that happens to be, if you look here, okay, and the probabilities are multiplied. Yeah, the moment you talk about this AND, it has to the probabilities will be multiplied. So 0.9 times 0.8, 0.99, and that comes out to be 0.713. Yeah, now this is all given, but the interpretation is very helpful. First, a thing that you have to always remember is anytime the system is dependent on component A, component B, and component C, all of them working at the same time, the resulting probability is less than any of the individual probability. Had it been dependent on only department A, you would have had a chance of 90% success rate. Had the process been dependent on only person B, who comes up in the office 80% of the time, we had a higher chance of probability. Component C or department C or a person C or a process working with a success rate of 99% of the time. But still, since we are talking about all of these working successfully, the resulting or the common success rate is 71.3%. Okay, now the contrary would be if we were to talk about redundancy, which means either component A has to work, or component B has to work, or C has to work. Okay, in those cases, any of them was to work, you will have a resulting output, correct? So if you were to go this way, and this way, such that you have a resulting output. So if either of these were to work, in those cases, you would be adding the probabilities. Now, how we will add, I'll show it to you in a minute. But the next thing we need to know about the failure rate is first thing is the percentage, which is common. We understood number of failures divided by the number of units tested, not all of them, but only the number of units that were tested. And then you represent it in terms of percentage by multiplying 100. Now, the second valuable number is the number of failures divided by the unit hours of operating time. This is helpful, for example, if you were to talk about, let's say, airplane or motors or cars. If everything else being the same, then we have to talk about the failure rate as number of failures divided by the number of unit hours of operating time. Now, why do we talk about operating time? This is key here. For example, if a car, let's say this is 2017, so if we had a car from year 2012, there's a car that has been driven 10,000 miles a year. So for the last 5 years, currently it has 50,000 miles on it. There's another car, exactly same everything, same type, same model, same color, same motor, same capacity, same brand, but it's been driven only 1,000 miles. Then theoretically we should have a higher reliability on this one. Why? Because it has less operating time. Okay. However, in terms of testing, the number of failures are only divided by the number of hours of operating time, not the full age. Okay, this 2012 with 1,000 miles on it might be better than let's say 2016 with let's say 30,000 miles on it. Okay, possible. So that is why this operating time is key. Okay, one additional information that this number reflects, which is more commonly understood by the general public, is the mean time between failure. Okay, if you were to take reciprocal of that, then that gives you the mean time between failures, which means if you know this number, then you can say what is the average amount of time that this component would go from time 1 to time in future, let's say T2, before you will encounter a failure. This is good for, let's say, if you were to install any safety valve on a gas heater in the house. What is the amount of time that it would run smoothly, let's say anywhere between 1 to 3 years before you have to regularly replace the valve? On an average, this mean time between the failure gives you an idea as to how safely you can sleep without having to worry about changing it every month or every 6 months or every quarter, instead of once every 3 years or once every 10 years. For example, fire alarm on an average in California, they are recommended to be changed every 10 years. How do they know that? Somebody should have tested or would have tested the number of failures divided by the number of unit hours of operating time, and that gave them high enough value for mean time between failures, such that they can confidently say that one fire alarm, or generally any fire alarm unit, is good for 10 years. Yeah, so that is the applicability of this maintenance and reliability concept. Okay, then there are a couple of other things that are important in this case. For example, the predictive maintenance versus preventative maintenance. Predictive maintenance is when you try to predict when the failure is likely to happen, and then you spend on the cost of replacing or making the maintenance. The preventative maintenance is usually cheaper, however, to an extent. For example, if you were to change the oil servicing of the car, it's recommended once every 5,000 or 3,000 miles, however the case may be. But it's an unnecessary added cost if you were to do that every week or every month, okay, or every quarter for that matter. So in those cases, I mean, those are smaller concepts, but there's always a trade-off. To an extent, let's say, if you were to talk about the commitment towards the maintenance versus the cost, initially the preventative maintenance, the more you do it, the more your cost is. Your breakdown maintenance cost goes down over a period of time at a decreasing rate. So it goes down, but not by the same amount. So the optimal point is somewhere before the actual breakdown happens, because if the breakdown happens, then it's difficult to account for the sudden change in the production schedule. Okay, so the next thing, predictive maintenance, already mentioned a little bit, but predictive maintenance can be thought of as the predictive maintenance can be thought of what is the probability of the failure, and the not only the probability of failure, but at the time. So this is probability of failure, and this is the probability of failure when you did not detect, because that's when the trouble is going to happen. If it failed when you did detect it, then you will probably be okay, because you would have made some backup plans around it, right? So this is negative, this is in a way negative, yeah, probability of failure times, so because it's time, you can say probability of failure and the probability of us not detecting that failure. If you were to combine this probability and subtract that from 1, that's your effective reliability. So this is failure, this is failure. If you were to subtract that from 1, that gives you the opposite of failure, which is reliability. Okay, now Control Shift D, and let's talk about the redundancy, for example. Okay. Where is it? Okay, there. So if we were to talk about, you remember when we talked about and this, and here we talked about this. Now let's talk about this one. First thing is, if the component A was to work, we will have an output. If the A does not work, but B does work, we will have an output. In this case, at this point, yeah, we can go to the next C as well, but at this point, to keep things simple, the first thing is, what is the probability that we will have an output at this time when the A did not work but the B did work? The resulting would be, let's say for the A is 0.9 plus the probability of success for B, which is 0.80, times the probability that you'll end up using B, which is you'll use B only when the A fails. A will fail when? 10% of the time. which is 1 minus point, I mean in a way the probability of success subtracted from 1, that's the probability that A will fail. Okay, so in this case you will have, let's say, 0.90 plus 0.8 times 0.1. Yes, so this comes out to be 0.90 plus 8 ones 8, 0.08. So you will have 0.98 as the probability of success if you were to talk about the system A and B. Now the key takeaway point is that the resulting probability of success or the system working is higher than any of the individual probabilities of success. Yeah, so A had 90% success rate, B had 80% success rate. So this is like saying at any given point in time I will have 2 security guards ready. Even if one fails, the second one will be able to shoot the bad guy. Yeah, or if you're saying if I need a light, then I have 2 flashlights. The first one, let's say from one company A, the second one from company B. The company one flashlight works 90% of the time, the second company works 80% of the time. The probability that I'll have a light when I need one, at least one of them will work, and therefore I will have a light. Therefore the probability, combined probability, is that there's a 98% chance I will have a light when I need it if I was to keep a flashlight from company 1 or company B. Okay, oops, dropped some. Now let's look at some of the numerical example to get a little practice on this. So let's talk about one of the end of the chapter problems from 17. We are given about the information about the heart pacemakers that were installed. Wherein medical equipment manufacturer subjected 100 heart pacemakers to 5,000 hours of testing. Okay, so remember, keep this in mind. We are talking about the number of unit hours of operating time. Okay, so first things first, halfway through the testing, 5 pacemakers failed. Okay, so 5 pacemakers failed out of how many? 5 failed out of 100 that were tested. Okay, now this was a little too early. Oops. So 5 failed out of 100 tested. Now this is in number, this is in number. So if you were to divide this by this and you were to represent that in the percentage form, that comes out to be 5%. Yeah, so this is already in percentage, you see here. Now the number of failures per unit hour, we need the number of hours of operating time. Okay, so first let us calculate the operating time for 100 heart pacemakers, which were all subjected to 5,000 hours of testing. So first let's say there were 100 pacemakers. They were all tested, subjected to 5,000 hours. So had none of them failed, the operating time would be what? Let me bring this here. Okay, so operating time would be 100 times 5,000. Yeah, this is the total possible time. Sorry, let me correct this here. So total time. Now some of them failed though. Yeah, how many failed? 5 of them failed. When did they fail? They failed halfway through the testing. Yeah, so 5 of them failed. When did they fail? Let's do this divided by 2. Yeah, so let's say non-operating time is what? 5 of the pacemakers who did not work after 2,500 hours. Yeah, therefore operating time should be the total possible time minus the non-operating time. That's the amount of time we have as a working time, correct? So if we want to know the number of failures per unit hour, which is given by the number of failures here, yeah, divided by the number of unit hours of operating time, now we can say equals to 5, which is the number of failures, divided by the operating time, and there you have it. So this is how we would calculate the number of failures per unit hour. Therefore, what is the time? Again, this is in per unit hour, right? You remember this was all in hours, this was in hours, this was in hours. This and all these, yeah, these are all in what units? These are in hours, yeah, that's the time. Now therefore the number of failures per unit year, yeah, would be equals to this divided by 365 days in a year times 24. So we are looking at 0.8 failures in a year, because this was an hour. So this is how many failures we are looking at in a year out of let's say at the rate of whatever this medical equipment manufacturer is making. Now, as of now, the general public would say, oh, that's pretty small, therefore it's pretty good. But how about if we were to look at it from the perspective of 1100 people who do receive heart transplant from the device that was manufactured by this company? Then in 1 year we can expect, out of those 1100 patients, we can expect these many failures. So if 1100 people were to receive the pacemaker implants, we would have 98 people potentially facing death, because there would be 98 pacemakers that would fail. Yeah, now that's the gravity of the situation, and that's where the importance of maintenance and reliability comes into the picture, and why is it so important for us to know those things before any damage is done. Okay, now on a similar note, we have a different problem, slight variation. We are talking about the hard disks here. Okay, so let me get this out of the way. So we are talking about the hard disk, where some manufacturer wants the mean time between failure of at least 50,000 hours. So on an average, the manufacturer doesn't want their hard disk to fail before 50,000 hours of operating time. From the recent test results, 10 units were subjected to the test. So I'm going to start getting the numbers wherein I can I can use them. 10 units tested. 10 units tested. One failed at 10,000 hours. So units failed at, there are multiple of them. So one failed at 10,000 hours. The second one failed at 25,000 hours. The third and fourth one failed at 45,000 hours. Yeah, the remaining units were still running at 60,000 hours. Okay. Determine the following: the percentage of failure, the number of failures per unit hour, and the mean time at this point in testing. Okay, so first things first, percentage of failure is equals to the how many failed? 1, 2, 3, 4. Yeah, total 1 failed, another failed, and then 2 more failed. So 4 divided by 10, that's 0.4. I'm gonna show it as percentage, so 40% failure rate. Now, in order to calculate the number of failures per unit hour, again like this, yeah, number of failures per unit hour, we want to calculate the operating time. So there are few ways to do it, or two ways to do it. Okay, one, 10 units were subjected, of which 4 of them failed. That means 6 of them worked just fine, correct? So let me bring this over here. So 4 of these failed at these specific hours. So 6 of them were working just fine. 6 of them were working just fine. For how long? 60,000 hours. So, but we are dealing with the testing duration of 50,000 hours. So we will limit that. We will limit ourselves to this number. So if 6 of them were subjected to 50,000 hours. Let me get rid of this number, even though this information is given, but we are not going to use it. Let me do this. Okay, and then like that. Okay. So let us focus on the operating time. So operating time. So this unit failed at what, 10,000 hours. So it operated for this, and I'm going to freeze it so then I can keep using this. F4 minus this. So it worked for 50,000. The second one similarly worked for 35,000 hours before it failed at this time. Similarly, this one worked for 15,000 and 15,000. Yeah. So sorry, my bad. This should have been non-operating time. Yeah. Everybody else was still working. All those 6 units were still working at 60,000. Yeah, that's the information given to us. So if we were to say equals to 10 times the 60,000, this would have been the total time had all of them worked. But we do know that the non-operating time total for the 4 units that failed is this 115,000 units, right? So the first one failed at 10,000. So this is the only time it worked. So the total non-operating time is 50,000. So either we sum up all these non-operating times and subtract this from 600,000, we should get the total operating time, correct? Yes or no? So this is operating time. Or a second way to calculate this would be if this is, let's say, let me move this over here. Okay, now if I was to say sum of the operating time for the units that failed, 125, what is the operating time for the other 6 units? The operating time for the other 6 units is 6 times 60,000. Yeah. So if you were to add up the operating time for the 4 units that failed plus the operating time of the units that did not fail, you still get the same number. Yeah. So these are the 2 possible ways. However you do it, it's up to you. Now we have the total operating time. We know the number of units failed is 4 divided by the total operating time. So this is going to be a small number. So let me bring up a few decimals. Okay. Now again, for a common man, this would be a very small failure rate. But the bigger picture is brought to light by this mean time between failure, which says at this point we will have oops, why is it like that? Okay, well, we don't need that many. Okay, cool. And we want this in commas. Okay, so the mean time between failure, the units for this would be hours. The mean at this current testing information, this manufacturing, the mean time between failure is 121 hours, 121,250 hours before the hard disk would fail. So it is way above than what the manufacturer's target is for 50,000 hours. So instead of 50,000, it's currently at 121,000 hours. Okay. Now then comes the next type of variation, wherein let's say insert. Okay. Now we are saying what is the reliability of the following parallel production process. So the first thing is, let's say if the process in a hospital, you can let's say talk about, let's say, a single person who is trained in multi-skill or multi how to say processes that the patient needs to go through. Or if that person is not there, instead we need two different type of people, let's say somebody at the reception and somebody in the radiology to do the, let's say, x-ray or something. So both these people have to be there in order for the patient to get the service. Or in terms of manufacturing, you can say either somebody goes through a certain type of production process that takes care of two different other processes. So this would be more like let's say peeling and chopping before a product comes out, and the other one is an automated process that replaces the peeling and chopping, and your product is finished. Okay. In this case, we are given the probability for R1, R2, and R3 as 0.95, 0.90, and 0.98. Okay. So why is it like this? Okay. Let me write down the numbers where they're usable: 0.95, 0.90, and 0.98. Okay. So in order for us to calculate the relation of R1 with R2, so before we can solve this and this, first we want to have a resulting value for the R2 and R3. Okay. Now R2 and R3 are in series, which means both R2 and R3 have to work for this leg to be useful. Okay. So the combination of R2 and R3 would be 0.90 here, 0.90, and this one R3 being 0.98, and because both of them have to work for a successful result, we will multiply these. Okay. Then whatever the combination of that happens to be, we will treat that in parallel, or how I'd say, or R1 has to work. So either the system of R2 and R3 has to work, or R1 has to work. In either case, we will have a working system. Okay. So let's see, first we calculate the resultant of R2 and R3. Okay. So R1 we'll take into account later. First is R2 and R3 both working equals to 0.90 times 0.98. Simple. Now, as a reminder, the combined probability of both R2 and R3 working is less than the individual probabilities. Yeah. Okay. Now R1 has a probability of working 95% of the time. Now the combined probability that R1 or this R2 R3 working is equals to the R1 working plus the probability that R2 and R3 will work when R1 will fail. Okay, so 1 minus 0.95. Okay, that's 0.9941. Now again, the key takeaway point of R1 having in parallel or in as a redundancy with the system of R2 and R3 is that the combined probability is higher than either of them individually. So if we had two people who had a probability of working 0.90, 0.98, the combined probability is 0.88 that both of them would work. This happens to be less than either of them individually. However, when we have a backup, when we use this system as a backup, when most of the time somebody who works 95% of the time is there, the combined probability that somebody would get the service is higher than any of them individually. Okay, so 0.95, 0.88, when the combined one is 0.99. Okay, this is also the reason as to why, let's say, you have a backup of batteries, let's say in the car, such that the combined probability of car starting is higher than if only one of the batteries were to be present. And just as a reminder, you can remember from this one the probability of first component working, which is R1 in our case, this one, yeah, plus the probability of second component working when the first one fails. Okay, so here, so in our case, the probability that R1 would work is 0.95, and then the second component, which we've already calculated the combined for R2 and R3, is 0.882. So 0.882 times 1 minus 0.95, correct? Yeah. And let me just check, did I do that right? Yeah. Yep. Okay, cool. So similarly, let's do one more type of problem, and I'll give you an alternate way as well. So the first thing we need to, in order to solve this, is first we want to solve this system, because this is this has redundancy. Either this has to work or this has to work. Once we have the combined one, then this one, R1, and this system and R4 has to work. Okay, so this is how it looks like. So let's see. At this point, you can either say R2 or R3 works. So the let me write them down where I can use their values here. So 0.90, and this one is 0.85, and they're actually both same, huh? So okay, 0.85, 0.85, and then this one is 0.90, sorry. Okay, so one way to do this is wherein equals to, if you were to go by this, by this formula, if you were to go, can I show this both at the same time? Yes, okay, better. Yes, okay. So the probability that, or let me do this in this colored cell here. So the probability that we will use R3 plus the success rate of R2 when the R2 will fail, 1 minus R2. Yeah. Okay, so the combined probability would be 0.9775. Okay, therefore the combined probability that R1, the combined probability would be 0.90 times 0.9775 times 0.90. Yeah, because this and this and this has to work for the system to work. Okay, so let's see the combined probability. Therefore, we already have this as 0.90 given to us. This is 0.90 again given to us. This is too far away. Let me bring this here. Okay, therefore the combined result is 0.9 times this times this. So again, as usual, between these two there was a choice, so either this has to work or this has to work. The resulting probability was higher than individual. Okay, when we were talking this has to work and this system and this has to work, the combined probability is less than any of the individual values. You see that? So that's the takeaway point. That's what you have to remember as a manager. Now, told you I'll give you one more alternate way. So one way to do this, instead of remembering this, right, R2 plus R3 times 1 minus, one way to do this is, if you were to think of what is the failure, what is the probability that none of these would work if this one fails and this one also fails. Okay, so the probability that this will fail is 0.15. The probability that this one fails is also 0.15. So the probability that the whole system fails, therefore, is that this fails and this fails. In essence, 0.15 times 0.15. That gives you the probability of failure for R2 and R3. Okay, so this comes out to be 15 15s are 225, so 225 and 4 of them, so 0.0225. Now if you were to subtract this probability of failure, that both of them fail, then you will have the probability of this system not failing. That means at least one of them works, right? So if you were to do this 1 minus 0.0225, you will have the resulting value as 5, 927, 927, and 9. Okay, remember this is same as this one, correct? So that's another way of doing it. Whatever works for you, whichever way you like. This one is like doomsday, so if none of them work, then it's easy to add the failure rate. Also, if you were to go back to this, if you were to go back to our example, okay, yeah, this. If you were to go back to this, instead of calculating the probability by saying the probability of C working when A fails and B fails going this way, it keeps on expanding. Instead, this second method that I told you is easier, wherein you can say, right, the probability of this failing is 0.10, probability of this failing is 0.20, the probability of this failing is 0.01. Therefore, the probability of all of them failing is 0.10 times 0.20 times 0.01. Whatever the result is, you subtract that from 1 and you will have the combined probability that any one of these three components will be working, so that it becomes easier. Yeah, but that's just trying to make you guys a little fancier. So just to show you, R2 and R3 fail is 0.15 times 0.15, and yep, so the probability that both of these will fail is 0.0225. Therefore, the probability that none of, or at least one of them will not fail is 0.9775, which is same as how we got here. So however we got, how you want to calculate, whatever works for you, whichever method you like. So okay, bottom line, that's about it in maintenance and reliability. It's more about the explanation and the gravity or the applicability of the situations wherein the concepts from this chapter are useful. Hope you enjoyed. If you have any questions, feel free to contact me. Take care.